Day 2. I want to make sure I encourage you guys to stop my video to go ahead and work out the problems. I'm not going to be leaving time in my video for you to work on problems so that you can pause at your leisure and go ahead and work the problems out and then continue to go to my solutions. Okay, let's go ahead, and we left off at the last video on page this page here, which is, I guess, our page 6. What we did, I'm just going to review, was we did minimum sample size, and I did for means. This is the formula that you have the margin of error equals z star times s over square root of n, and the reason you're using z star and not t star for means is because you need n to find the degrees of freedom to find t star, and we're looking for n. Since we don't know n the whole time, I need to use a substitute, and z star is pretty close to t star, so that's why we're using z star. All right, and then for proportion, you're going to be using this formula that's always used anyway. And the trick on proportion, if you don't know p hat, if it's not given to you, you're going to use what we call a worst case scenario p hat, which is 0.5, because that gives you 0.5 times 0.5 gives you the biggest standard deviation possible, and you don't want a big standard deviation, so it's a worst case scenario standard deviation. Okay, so let's go ahead and start with this problem here. Continuing, this is a minimum sample size for proportion, so we know that I'm going to have margin of error equals z star square root p hat q hat over n. Again, I'm encouraging you to stop the video and do the problem and then go from there. So it says here at no more than 6%. So 0.06 is equal to, and 90% confident, I know from memory is 1.645, but I'll show you where I get that from. That comes from inverse norm. And I go to area 95%, remember, because the 90% is the 90% in the middle, and I have to include the tail because my calculator starts from here, but I don't want the left 90%, I want the center 90%, so I have to put 0.95 to calculate for the tail, 0 and 1 for the mean and the standard deviation. And then for p hat, q hat, it does give me, let's see if it gives it to me on this time. I have the manager car company select here, the estimate proportion who has 2 children. And so this one does not give it to me. So again, I have to use 0.5 over n. And then go ahead and let's calculate this. So I'm going to go to my calculator here. And I have, I'll just do nsolve so I can do it quickly. Algebra solve, and we're going to type in 0.06 equals 1.645 square root, and then this here, and I have 0.5 times 0.5, and I'm going to put it over n or over x. It doesn't matter which you use. And then, of course, I'm going to put comma n. And make sure your comma is outside of that square root. And so I get 187.9. So n is equal to 187.9. But in the case that you always do this, is you always are going to round up to the nearest one, and it's 200 is the nearest one indeed here. So, all right, next problem, self-selection issue. Okay, so if you notice on the next couple problems, it's a self-selection issue is a commonly asked question. And if you look at this, it says, you might want to pause this and read it, but basically it's telling me how I'm selecting the sample. And the sample is allowing the students to eat in the cafeteria, allowing them to choose which ones want to be part of this sample method. And so that's why that B is the one correct, but let's talk about why the other ones aren't correct, because each student leaving the cafeteria was randomly selected. They weren't randomly selected, actually, because you can see here, the students can choose whether to eat in cafeteria, all right? So they can choose, and this sampling method is biased because it's a choice here. A reporter of here has a reaction to changes of the menu in the cafeteria. For each student leaving the cafeteria in one 30-minute period, the reporter used a coin to determine whether to stop them or not. And so the problem is, and a random sample. So yes, I have a random sample. However, it's not a random sample of those eating in the cafeteria to begin with. So that's the problem, is that if I'm choosing to eat in the cafeteria and I'm asking about the cafeteria, then that's going to be an issue, that it's not representative of all the students in the school, because I am trying to see what is about all the students in the school. So that's the problem. If this population was just about students that ate in the cafeteria, no problem here, because it was random, everything looks good. I did a systematic kind of a sampling, but that's not the issue. I am trying to represent all the students in the school, and the only people I asked were those that were in the cafeteria, and they were allowed to choose if they eat in the cafeteria. Therefore, there probably is going to be some bias about if they're going to be in the cafeteria or not. All right, so this one here, let's check this one. Same idea. A program was intended to cure the person's fear of spiders that was offered at a local zoo. Volunteers of fear of spiders, again, volunteers, which means they self-selected. But the volunteers isn't necessarily the issue, it's how they're going to have the treatment. So watch, which include holding a spider for 15 minutes. 1 month after they complete the program, the participants were contacted and asked to survey about the program. Over 90% of them claimed said yes, they did a fear of spider. Remember, I'm based on the description of the program, which of the following statements is true. So when this says, because over 90% of the participants claim to be cured, the results prove, first of all, when you see the word prove, you know that that is not going to be correct. So I see that word and I say no way. Because over 90% of the participants claim to be cured, the results can be generalized. No, how do we generalize results? We generalize results. Remember, we can generalize things when we have a random sample. When we have a random sample, that's how we generalize results. And then when we have, for the next one here, because the participants were volunteers, the study is a census of all people. No, and that's not, a census is when I do all people, but I didn't do all people. So that's not even a census, so that's not true. Part D, because the participants were self-selected, a person's desire to be cured could be a confounding variable. Yes, that is definitely true. Because I am allowing myself, I'm scared of spiders, this program is going to help me out. And so I jump into the program and it helps me out. And does it help me out because the program's good, or does it help me out because I have a high desire to get over my fear of spiders? And then the last one says, because participants held the spider for 15 minutes, the study is an experiment and results can be generalized to the population. No, the way you generalize to the population, remember, random sample. Random sample generalizes to the population. Random assignment allows cause and effect. Okay, for histograms describing data, let's talk about a couple things on histograms. Okay, so for histograms, the one on the left is what is potentially in here. And I'm saying potentially in here. We don't know what data's in here. We just know 8 pieces of data are between 10 and 20. So I could have 12, 13, 13, 14, 14, 15, 18. That's 1, 2, 3, 4, 5, 6, 7, and then let's go with 19. So none of these are even equal to 10. I know that it has to be less than or equal to each one of these. Let me go ahead and put this, less than or equal to X and less than 20, because 20 is in this. If 20 exists, it would be in this one. If 30 exists, it would be in this one. Again, I don't know the specific data values. All I know is that these are the values here. So I don't know the minimum. I don't know the maximum. I do know that values are above. I do know that 60 is not included, because if 60 were included, it would be over here. All right, so that's kind of the general aspect of histograms. So to find the median of the histogram, I have 8 here, I have 2 here, I have 1 here, I have 2 here, and I have 8 here. So that's 8 plus 8 is 16, plus 2 plus 2 plus 1 is 21. So I have 21 values. I always say plus 1 divided by 2 gives me my median, because 22 divided by 2 is my 11th value. So my 11th value would be 8 plus 2 is 10 plus 1, and so my median is somewhere in this bin of 30 and 40. I don't know, but I do know that 30 is less than or equal to my median, which is less than or equal to 40, okay? So that's kind of how we're going to be doing histograms. So let's go ahead and look here. For letter A, the mean of the data A is equal to mean of B, and this says must be true. Now, it might be true, But we don't know that for sure, again, because we don't know where the data is. Let's say all this data is true here, and this data it's all over the place. We don't know where it is. So because we don't know what the exact data is, we can't say that. Same idea with the median. We don't really know what the median, we don't know what the actual data is, so we don't know. We know what bin it can be in. We could say the bins are equal, and we can say that, but we do not know what is the actual data. The range of the data is equal to here. Again, I don't know if these are all, maybe the smallest one, maybe they're all 19. Maybe I have 8 19s here. And, you know, I don't know. And this, let me see, let's say I have the highest one of may have 8 51s here. But then let's say I do have a 10 here, and let's say I have a 59 here. So obviously you can see the range is going to be not necessarily the same. Okay, standard deviations we can compare because we can see the spread. Most of the spread of this one is really, really tight, and this standard deviation is going to be less than this standard deviation because most of this spread is spread out. So we definitely can say that, yes, this one here, where the standard deviation of A is bigger than the standard deviation of B. Okay, let's go ahead and look at this one. This one was one that you guys had on your practice test last week. And we have the median price is not greater than $750,000. The minimum price is not greater, the minimum price, is $250,000. Again, we don't know that for sure. We just know it's included in this bin. Same thing with this one. We know that this is actually not the maximum price because that would be included in the next bin. So we don't know for sure what the value is in the bin. The median price is not greater than $750,000. Well, if I have 304 homes, remember I say 304 plus 1 divided by 2 gives me my median value. And so that's going to be 305 divided by 2. And so then that's going to give me, so when I do that, I'm going to have 152.5, which means it's going to be between my 152nd and 153rd value. Well, 38 plus, so I have my first 38 values here, and so from 0 to 38 values are here. Then from 39 to 38 plus 120 is 158. So I have between my 39th and 158th value here, and I'm looking for the value at 152 and 153. So I know that my median is indeed located somewhere in this bin. So yes, that is true. The mean is between 500 and 750. We do know, since I just located my median, right, and it's skewed to the right, we know that my mean is only going to be here or to the right. It's going to be further to the right than the median, so we definitely know it is not here. A little quick way to actually find the mean is you can actually take each one of those, I'm going to take each one on the left, 250 times 38 plus 500. I'm taking each bin on the left times 120 plus 750 times 82. All the way I'm going to go plus dot, 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 plus all the way to the end of 2250 times 1. And you're going to divide that by the total number of homes, which is 304. And that actually will give you the bin that the mean is in. All right, and so that actually will give you the bin that the mean is in, and you could see that it's definitely not going to be between 500 and 750. But if you're having trouble with spatially reasoning, you can actually quantitatively figure out what the mean, which bin the mean is going to be in. Upper quartile of the prices is greater than 1.5 million. Well, again, the way you would do this is saying, all right, when I have 304 and I divide it by 4 quartiles, that's going to be 76 values. I'm going to be 76 in my first quartile, 76 in my second quartile, 76 in my third, and 76 in my fourth. So I could look at the 76th value, which it says greater than 1.5 million, which is here, right? Well, clearly, that's not even 76, right? So it's going to be less than that because it's going to be in my 76th point from the top, which clearly this is not. Okay, let's look at transforming data and reminding myself how to transform data. To remind you how to transform data, remember what I have with mean and I have standard deviation. Okay, when I add, let's add data. Remember what happens, and this is going to be multiply. When I add data to the mean, I'm going to take the mean plus I'm going to put add C, right? Mean plus the C. Or subtract, either way, add or subtract. All right, so add C plus C, multiply C, MC. Standard deviation, remember if I have here's my data, 1, 2, 3. You can see when I add, let's say add 2 to everything. This is going to be 3, 4, 5, and you can see that, look, the distance between, remember standard deviation is distance from the mean, you can see this is 1, this is 1, and this is still 1. This is still 1. So adding did not change the standard deviation at all. No change there. But multiplying, if instead, let's start again with 1, 2, 3. Let's now multiply by 2. 1 times 2 is going to give me 2, 2 times 2 is going to give me 4, and 3 times 2 gets me 6. And so you can definitely see that, okay, now this is plus 1, but now what is this? Plus 2, plus 2. So, oh, it multiplied by 2. So it's also going to multiply, get the standard deviation times C. Or divided by. Multiply, divide, and add and subtract also. Add, subtract. Okay, so let's go to this problem here and solve it. So this one's telling me what happened. An auditor determined that there was an error in the reported areas, that all the areas should have been 100 square feet greater than reported. So I just basically took all the data and I added 100 to it. And so this is what happens when this top one here. So basically only the mean's going to change, not the standard deviation. So, and then the spread. Let's talk about spread. Yeah, so spread also is just like any spread, standard deviation / spread, because standard deviation is part of spread. So that would be like my IQR would also react the same because it's just the spread, how far spread out. The range would act the same. Any point is going to act like the mean. So if I say, I want the second point of the data, what happens? Well, whatever happens to the data, if it adds, subtracts, multiply, divide, it's going to change however the data changes. However, a spread, when I'm subtracting 0.4 minus 0.2, and I just add 2 to both 0.4 and 0.2, there's no change in that spread. So we're going to look here, and we're going to see the original IQR was Q3 minus Q1, so 1806 minus 1704. Which is going to get 102. So that's going to be either this one or this one, because it just, all that happened is I added 100 to the data. However, and then of course the standard deviation is absolutely the same as well. It gives you the standard deviation, and that's going to be the same. Okay, again, take a minute and do this one, and let's go ahead and solve it once you get it. All right, I have 4 apples, 6 pears, 1 basket, and which one's the closest to the standard deviation of 1.9, of standard deviation of W. Okay, so since I am adding them, remember when I add the standard deviations, I cannot add standard deviations, I have to add the variance. So my apples, I have 4 apples, and so standard deviations, I have 0.2 squared plus 0.2 squared plus 0.2 squared plus 0.2 squared. Right? 4 of them. So to save us time, I'm just going to say, okay, I think you guys understand that this is 4 of them because I have 4 apples. For 6 pears, I have 6 times, same thing, 0.18 squared. Okay? And then, of course, I have 1 basket. So in our calculators, we're going to go ahead and solve the square. So we have 0.2 squared times my 4. And then, of course, my 6 times my 0.18 squared. And then, of course, times plus my basket. Oh, which I left off here, sorry. My basket, 1 basket. So 1 basket at 1.88 squared. And that's my variance. And then I have to find the square root of that, choom choom, and I indeed get the answer of 1.97. Okay? Next one, go ahead and try this problem. And it wants the standard deviation, it wants to subtract the standard deviation, but remember we can't subtract standard deviation, we can only add the variance. Remember, again, when you see the data, if you need to see an example, you're going to, because if I have 1, 2, 3, and I have 2, 3, 4, and I subtract these data, watch what happens. I have 1 minus each of these. 1 minus 2, -1, 1 minus 3, -2, 1 minus 4, -3, and keep going for all of them. 2 minus 2, 0, 2 minus 3, another -1 in here, 2 minus 4, another -2 in here, 3 minus 2, 1, 3 minus 3, a 0 in here, and 3 minus 4, another -1. You can see what happens is the data actually gets further apart. The data was on each of these, this was only 2 apart, this was only 2 apart, but you can see what happens to the data. Now this is 4 apart. So you can see that that's it's going to actually spread out more. So let's go ahead, and you have to make sure they are independent in order for you to be able to do this. So for transforming data, we have a mean, and we're looking for the standard deviation, so I don't really need to even use the mean. So I have a standard deviation of 15 and 9, so 15 squared plus 9 squared is going to get you your data. And the square root of that, and that gets you 17.5. Okay, transforming the data here. Same thing. This one here is multiplying by 3 and adding 10, and I want the variance of the transformed sample. The original variance is 4. Remember, variance is standard deviation squared. So I want the variance of the transformed sample. So I have the first thing I'm going to do is I'm not going to add 10 because remember it's spread, and spread is not affected by adding everything to the data. So if I'm going to go ahead and first of all find my standard deviation, which my standard deviation is 2. So I'm going to do it. How do I multiply? How am I going to multiply this one by, so if I multiply my standard deviation by 3, it's going to be 6, right? But it wants variance, and the variance is going to be 6 squared, which is going to be 36. Okay, so that's the first step I did. I put standard deviation, and I said, oh, what am I doing? I'm multiplying it by 3, but I'm asking for the standard deviation, or excuse me, the variance, not the standard deviation. All right, so for this one, this is asking the question, which of the following statistics on the field has the same value before the adjustment? So what did I do? It subtracted 3 from everything. So we know the median's going to change by subtracting 3. We know the mean, all of these are values, and they're going to change. Each are individual values that are going to change. They're going to all subtract 3. The interquartile range is spread, and spread is the only thing that does not change when I subtract values. All right, so for number 8, we are going to, now we have Fahrenheit and we are converting to Celsius, and I would like to know what happens for just the standard deviation. For just the standard deviation, remember what we're doing is we're just literally going to be putting it in. And so I would just be putting in 9/5 times 0.4, and that's it. I'm not going to be adding the 32. So that's just B. Transforming here, and this is asking for mean and standard deviation, new mean and standard deviation. We have an old mean of 47. We have an old standard deviation of 14. And if 4 is added, so I'm adding 4. Remember, this does nothing. And so I'm looking for a new standard deviation that's going to be 14, so we know it's not going to be any of these. And the new mean obviously is not going to be the old mean, so we know that's not going to be 47. So this one by default is going to be A, but yes, 47 plus 4 is 51. Okay, remembering expected values. Expected value is just another word for mean. And we are going to see, and then we're going to be using transforming data through this. So expected value and standard deviation. Expected value, remember, is the mean. And standard deviation for this particular problem here. So it says, assume X and Y are independent. What are the expected value and standard deviation of points per player? So for this one here, I have 9.5 is the mean of this one and 12.9 here. And it says, in order for me to get an expected value per player, then what happens is, let's kind of go through and see, this is what happens. So in a certain computer card game, the player is awarded 5 points for each card that's moved in the correct position, and penalized 10 points for each minute that it's played. let the random variable x represent the number of cards moved in a correct position, and let y represent the minutes the game is played. The means and standard deviation of a random variables for a particular game are showed below. So you're going to see that I get 5 points awarded for correct position, and then I get penalized 10 points for time. And you see X is the number of cards, so this is cards. And then Y is the number of minutes. Okay, so I have to multiply my, my mean is going to be, I'm going to have 5 times my 9.5 for my mean, and then I'm going to subtract that from 5.4, my y, times 10. The reason it's subtracted is because that's going to be a negative 10. And so I'm going to get on my mean, I have 5 times my 9.5, and I'm going to subtract it to 5.4 times my 10, and that's where I'm going to get negative 6.5. So I know these are all not correct. And so now I'm going to do something similar for the standard deviation, but of course I can't subtract the standard deviation. I'm going to add, and I have to do the variance. So I'm going to do, again, I'm going to say, okay, I've got for my standard deviation, something very similar in the aspect of I say, all right, I've got 5, because I've got my 5 points for each one, and I'm going to, each particular one, I'm going to, since I have 5 separate ones, I'm going to go ahead and multiply that by my 12.9 squared, and then of course adding it to my my y, which is going to be times the 10. And then of course you're going to find the square root of that. So let me show you. In this one here, and so you end up getting 65. So the way it would work out, though, is going to be 5 squared times 9, not 9.5, sorry, times 12.9 squared. And the reason being why I'm squaring it is because I'm taking one player, and I'm multiplying his points by 5. I don't have 5 separate players. If I had 5 separate players, I would not be squaring the 5. And I have to add, and I'm going to be doing 10 squared, same thing, 1.1. And I remember, I'm adding and not subtracting because I never can subtract the variances. And so and then if you do this math, that's what you're going to come out with, is 65.5. Okay, let's go to the next one. The random variable is normally distributed, so that's important. Mean of 5, standard deviation 25. Random variable is defined by 2 plus 4x. What's the mean and standard deviation of y? Okay, so I'm going to, I've got, with my mean, I'm going to do this. 2 plus 4 times 5. With my standard deviation, I'm going to ignore the 2 and just do 4 times 25. And that should get you your 100. Okay, for this next one, we're going to go very quickly through this. Box plot, the main thing, I just kind of want to make sure that I point out to you, obviously this is the minimum. This first one's Q1, this is the median, this is Q3, and this is the maximum. If there's any outliers, you see little asterisks or whatever, you have to remember the outliers. The outlier is Q3 plus 1.5 times IQR for the upper ones, or Q1 minus 1.5 times IQR for any lower ones. Remember, IQR is Q3 minus Q1. And remember, the other big thing that they trip you up on is that the same number of values, if I have 100 flights here, then there's 25 here. There's 25 in this quarter, 20, because these are just quarters, and 25 in these quarters. This quarter here is just jam-packed and everything's very similar, and this one here just has a larger variability. But it just means they're in quarters, so remember that for the box plot, because that's an often question that's missed, is they say, oh, there's more data in this one than there is this one, and no, there's not. So that's the main thing for here. So I think you guys can handle these pretty well. Go ahead and kind of take your time and go through them. Let's look at this one here. If there's anything, nothing really is bigger. This answer is E. The difference between the median and lower quartile for the on-time arrival is less than 2. And that's median is this here, and Q1 is here, and that's definitely less than 2. All right, I'm just going to give you the answers for these. Stop this and go ahead and go through these to make sure that you have that. And this is, yes, they have the same number of data points. We cannot justify that because we have no idea. We don't know. Comparing the box plots on this one for number 2. 50% is at the median, so that's going to be E. So again, take your time to look at these. But I don't want to take too much time on these because they're pretty simple with comparing. But these should be easy points. You should get 50%. Remember, this is 50%. That's 50% because right in the middle. 50% of these right in the middle. 50% of these right in the middle. Okay, because box plots are literally like this. 25%, another 25%, another 25%, another 25%. Okay, go ahead and stop and do this one. At least half the women had a higher pulse rate than 3/4 the men. When you say this, you go, yep, there's half the women, and there's 3/4 the men right there. So yes, that was C. Stop and do this one. And then this one, you'll get in both tournaments, at least half the golfers have completed the tournament with a score less than 288. So here, we're at half of them, and there's 288, so yes. 19, again, stop and do this one. IQR of the brands classified as healthy is greater than IQR brands regular. And IQR is this here. So you can see, obviously, subtract those pieces of data. Okay, identify in ho and ha. So let's go to something here that's a little bit more challenging. So for ho and ha, the manufacturer of balloons claimed that the proportion of balloons burst inflated diameter to up to 12 inches is no more than 0.05. Okay, some customers, so this is just how big the balloons are, so we don't need that, but no more than 0.05. So some customers have complained the bursting balloons are more frequently if they want to conduct an experiment to say the manufacturer's claim, which, by the way, the claim is no more than 0.05. So no more means that I'm saying that is it actually, to test the claim, we're going to do this. We're going to see if it is bigger than 0.05. That's my ha. Ho is always an equal sign. So you know it's not this one because it's not that. It's not this one because it's not that. All right. So you see here, this here did not have a not equal to in the original. There we go. That one did not have a not equal to in the original. There you go. All right, so I'm testing the claim, and the claim is I'm saying that it's equal to about 0.05. And I will tell you that it's not going to be more than a 0.05. And we're saying, hey, I have evidence that it is bigger than 0.05, so that's why it's going to be the greater than, not the less than. The less than would be showing the manufacturer that the customers aren't complaining if it's less than 5%. Customers only complain if it's greater than 5%. So that's why it's going to be B. Remember, what the question is what the ha and the ho is always an equal to. So we're going to have the researcher's claim on this one here. Before I even read it, I'm going to cross this one out and cross this one out because of these two here. And I look, and everything else is valid. So I'm now going to read it here, and I see it says it wants to determine convincing statistical evidence that more than 50% of the households, a charitable destination, and P is equal to the households. So yes, I am indeed going to say this one here. I look here and I see, oh, there's a problem. This, and this. Remember, your ho can only be for the mean, mu, for the mean. For the proportion, it's going to be P. For the Linear regression, you're going to have beta, but it has to be a parameter. And X bar are samples, and those are not parameters. So A, B, and C are not correct immediately. So then I can say, I just read the question, and it says, if the group can studies to investigate its beliefs, which the following hypothesis should be tested to claim that the actual mean flight is greater than 38. So I am testing this. Okay, now I got to identify ho and ha, and I see that I'm first of all going to identify this as, notice it says is paired. You're going to have, and it tells you mu d right here. It says mu d, so literally do not use anything else than mu d. It gives it to you, all right? And the ho is always going to be mu d is equal to 0. The ha is, that's what we're going to determine and see what it says in the question. So in the question, it says, which is the following, because we're trying to represent to see if the shaving, if shaving before, so I'm trying to say if it makes me faster, right? Well, obviously this is not faster, this is different. And I'm saying, is the difference, meaning before minus after, is it bigger than 0? Because does before minus after, well, if it's bigger than 0, that means after I had a faster time. So yes, that's why it would be bigger than 0. Okay, for this one here, we're going to do ho and ha. So the first thing I'm looking at is anything that is not correct in the A, B, C, D, or E. And it's like, okay, they all look okay without reading the question. So now I can go ahead and read the question. Unfortunately, there's not anything that I can actually cross out at this point until I start seeing what type of test it is. So when I say so the first thing I'm going to do is and check, do I think it's, oh wait, hold on, there's one I can do. Look, 2 sample Z-test, that one I can set out because we know that Z is proportion, so I can cross that one out. But for this one, I don't know yet. I can cross out once I'm a little closer, but I'm basically what I'm going to be checking is it 2 sample or matched, and then I'm going to see, is it not equal to or is it less than? And that's what we're going to figure it out. Okay, so let's read it. From a random sample of 50 people, sitting pulse rates and standing pulse rates were measured for each person. Each person. So therefore, I'm already saying, okay, we're at matched pairs. So let's determine whether sitting or standing will be measured first. Sitting is here, standing is then here. And mu d, oh, it says mu d right there, and that mu d means paired. So immediately when I see that mu d, I didn't see that mu d in there, I know that this is definitely going to be one of the ones. And then which of the following, and so we're trying to see if it actually is, if it reduces it, if there's, if the mean of the differences between sitting, if there's a difference, that's what it says, is difference would be not equal to, and so that's why it's going to definitely be D. Okay, 2015, 95% confidence interval. This is all interpreting confidence interval. Okay, so for confidence interval, I want you to remember we're going to say, is the population in the interval? That's what I'm looking for. I'm going to say that I am blank % confident that the population is in the interval. And when it is in the interval, when it actually is in the interval, we are going to say that is a fail to reject ho. Because that's basically saying, look, this is what we're expected to be true. When it's outside the interval, that's when, and when we look at this, here's my confidence interval. This is my confidence interval here, right? And these are my little rejection regions out here. So when it's outside the interval, it's reject. When it's inside the interval, it's fail to reject. So let's remember that, and let's go ahead and see here. So yes, let's look at some also confidence interval is not probability. The probability that the population is in the interval is either 0% or 100%. It's either in it or it's not. The confidence interval is made up of the sample, and I'm asking again, is the population in the interval? And the samples have to be same size. Samples, same type, same size. Can't be all samples. Those are the key things to write about confidence intervals. All right, let's look at number 30 here. 95% confidence interval for the mean time a volunteer fire company will respond is determined to be this here. Which of the following is the best interpretation of the interval? Okay, so I'm 95% confident. There we go. So this one started out 5% of the time, and as you see, I've already written, confidence interval is not probability, so that is not going to be correct there. For part B, the probability, no, it's not there. Okay, let's go ahead. 95% of the time, the mean responses is, that's too deterministic. Remember, this is our estimation, what we expect to be true, we are 95% confident that the mean time for responses is between, yes, this sounds very reasonable. That's exactly what I'm looking for. The population is in the interval. And this one says we are 95% confident that a randomly selected time for response, no. We are looking for the mean time, the population. This is saying one of the times will be between 2.8, and that is not right. It's the population is in the sample. Number 15. A polling agency conducted a survey by having 100 random samples, each consisting of 1,200 United States citizens. The citizens in each sample were asked whether they were optimistic about the economy. For each of the sample, the polling agency created a 95% confidence interval for proportion in the United States were optimistic about the economy. Which of the following statements was the best interpretation of the 95% confidence level? Okay, so we can kind of, without even reading this, honestly, we could have crossed stuff out, but I'm going to go ahead and go from here. With 100 confidence intervals, we can be 95% confident that the sample proportion of the citizens are optimistic. No, not sample proportion. What are we looking for? We're looking for population. We would expect about 95 out of 100 confidence intervals to contain the proportion of the citizens in the United States that are optimistic about the economy. Yes, because this is describing my population. We're expecting about 95% of them to contain that population. So yes, this one would be correct. Let's talk about why C, D, and E are wrong. We would expect about 5 of the 100 confidence intervals to not contain the sample proportion. There we go again. Sample proportion should be population. Of the 100 confidence intervals, 95 of the intervals will be identical. Nope, we're not identical. They're going to be similar, but not identical. The probability, we've got probability. Okay, so those are kind of, you can even go through these. And in fact, let's go through these A, B, C, and D without reading it and try to see. We have to know what the population is, which is the population's U.S. living adults that are satisfied with their health care plans. Okay, probability, nope. Already started out here. Okay, I'm going to skip to C. Approximately 95% of random samples of the same size from the population will result in the confidence interval that includes the proportion of adults in the sample that are satisfied with their health care plans. Okay, first of all, will result. We don't know for sure that that's going to result in the confidence intervals, but look here. I have population, look at this then, the proportion of all adults in the sample, and that's the thing, is I'm not in the sample. So will result is kind of question, but it's okay. But that's the problem is it's adults in the sample is the problem because that is not my population. I'm looking for the population, which is all the United States. Because it was randomly sampled, so I could do that. Approximately 95% of all random samples of adults, now again, all random samples, nope. Only the random samples of this of a similar size. And this one again, all random samples, nope. So let's read why this is good. 95% of random samples of the same size. There we go. Same size of the population. Yep, from the population. So these other ones, the problem was, of course, all random samples. I need of the same size. Will result in a confidence interval that includes the proportion of all living adults because I can conclude to all adults, not the adults in the sample. The adults in the sample is if I didn't have a random sample. But because I had a random sample, I am able to do, because it says I have a random sample. And random sample allows me to conclude to the entire population. All right, conclusion from p-value. Remember, p low, reject ho. P lower than alpha, reject ho. So we have a p-value of 0.24. At any value, that's going to be a fail to reject because nothing's that big. So most likely, we're going to say the test was statistically significant. No, No, not statistically significant. So P low, reject ho means statistically significant. P high, fail to reject that guy, means not statistically significant. So we're saying when it's not statistically significant, this is what's happening. If this value is, let's say, 14, and I get a value of, I don't know, let's go with, let's say that's 2 standard deviations, or 1 of 17, right? And I say that, yes, we do believe that 17 is bigger than 14, but not statistically significantly bigger, because we're saying it happens in variation. Sometimes this value is 17, sometimes it's 16, sometimes it's 14, but that happens pretty often. So that's why that would not be statistically significant, because this would obviously give me a pretty high p-value. All right, so B says was statistically, so anything that says was, we know it's not. So these say not, so those are okay. Typically, the longest one's the correct answer, and in this case, it is indeed as well, but let's see what's wrong with C. C was not statistically significant because 2 times, all right, so 2 times 0.24 would be getting like a 2-sided test, but I don't know where they're getting that from, because it didn't really say anything about that, so that's not correct. Not statistically significant. If the null is true, one could expect to get a test extreme, at least extreme 24% of the time. This is the definition of p-value. Remember, if ho is true, we expect to get at least this percentage of the time. And finally, E, it's not statistically significant because if the null is true, one could expect to get at least 70% of the time. No, it should be 24%. All right, that is the end of my section 2. Go ahead, and I hope to see you go ahead and for section 3, make sure that you took notes on this and you upload it to Canvas for your note-taking portion of this assignment. All right, thank you so much.